Hello friends, welcome to a new session of engineering circuit analysis in my channel. Basically in this channel I bring electrical engineering lectures for the benefit of all of you, and we are starting with engineering circuit analysis. Now in the previous sessions we have discussed many concepts like node analysis, mesh analysis, superposition theorem, and all those important analysis techniques by which we solve electrical circuits. Now, in this session, we might be dealing with one of the most important sessions in electric circuit theory, which is a very useful technique. And why it is useful is because throughout the course of electronics engineer and throughout the course of electrical engineer, you might find some or other application of Thevenin and Norton equivalent circuits. In electronics engineers, when you analyze BJT circuits, you use a lot of Thevenin's equivalents. And in electrical engineering, when you use the analysis of induction motors or analysis of equivalent circuits of transformers, a lot of Thevenin comes into play. Now, before starting with the actual topic, let us give a little bit of credit to the people who have given us this theorem. Now, Thevenin's theorem was given to us by M.L. Thevenin in the year 1883. And this was given by E.L. Norton, and he is from Bell Laboratories. Now, that is enough of history. And basically, Norton is actually a corollary of Thevenin's theorem. So once you understand Thevenin's theorem properly, the generation of the Norton equivalent circuit is quite easy. Now, what is the motivation of Thevenin's equivalent? Basically, when you have a very complicated circuit and you want to analyze the current, voltage or power of only a part of the circuit or through a particular element, in that linear circuit, you can replace the entire circuit by a single independent voltage source and a series resistance, and you can keep the part of interest aside. So what does that actually mean? For example, you are having a very complex network. Alright, this is a very complex network inside the black box. Alright, and this is the circuit element which we are interested in. The RL is the circuit element in which we are interested. So analyzing and doing an analysis always on this particular complex network might be time consuming. So what Thevenin's theorem tells us that you can replace the entire complex network by a single voltage source with a voltage V Thevenin and a series resistance R Thevenin. And then here you are having your load resistance, which is unchanged. All right. So what is the meaning is that this complex network is electrically equivalent to this Thevenin voltage, which is in series with the Thevenin resistance. It is quite amazing, isn't it, that you can replace the entire complex network and then you can do all your calculations with only a voltage source in series with the Thevenin resistance. It is very interesting. Now, what is the Norton's equivalent is that this entire complex, this is the Thevenin equivalent. So what does the Norton equivalent tells is that you can replace the entire complex network by a single current source which is having a current I Norton, and this will be R Norton in parallel, and this is going to be your load resistance. So this is also electrically equivalent to your complex network. This is also electrically equivalent to the complex network. So this is the basic idea of Thevenin and Norton equivalent circuits. That is, you can replace a complex circuit by a single resistance, a single voltage, independent voltage source in series with the resistance, or a single current source in parallel with the resistance. The Norton resistance and the Thevenin resistance for a particular circuit will be exactly the same value. All right. So to understand this, let us take a small and very simple problem. All right. And we will not be using any fancy techniques here. We will be just using some simple source transformation. All right. This is the question here, right? So what we are going to do is that we are going to divide this into two parts. All right. So this is two parts. I am dividing a line. So this entire section will be network A, and this load resistance in which I am interested is network B. All right. So what does Thevenin's theorem tells us that the network A can be converted into a series voltage and a series resistance So this will become our network A, their electrical equivalent, and this is my network B, RL, which is untouched. So this is my network B. So let us see how we can use this, the techniques which we have learned so far. Now you can clearly see that this 12-volt source is in series, direct series connection with the 3 ohm resistance. Therefore, let me use a source transformation technique. So if I use a source transformation technique here, so what will I get? I will get a current source which has a direction like this. So the current source value will be 12 divided by 3, 4 amperes, and the resistance will be the same. I have discussed already source transform in the previous lecture. So if you have any doubts, you can go and see the lecture. So this is 6 ohms and this is 7 ohms and this is the load resistance RL. Alright. So this is my line which is dividing this. Now you can combine these two resistances, right? 6 is parallel to 3. So 6 is parallel to 3, that will be equal to 2 ohms. Alright. So I can combine these two. So I will get a 4 amperes here and this will be 2 ohms and this will be 7 ohms and this is my load resistor and this is the line separating the two circuits. Now 4 amperes is directly in parallel with the 2 ohms. Therefore I can do a source transformation here in which I can replace the thing with a voltage of 8 volts in series with 2 ohms. Alright. So here you are having 7 ohms. Here you are having RL. So this is the line separating. Alright. So finally what I get is that I get 8 volts. 2 and 7 are in series. So I get 9 ohms here. And this is my load resistor. So therefore the network A I have converted into a Thevenin equivalent, and that is in compliance with my definition also. I have replaced the entire network by a series connection of a independent voltage source and a resistance. So this is one method of solving. But however, unfortunately, all the circuits cannot be solved with a simple continuous source transformation and resistance equivalent circuits. You cannot do that because networks are going to be more and more complex. Therefore, you need to understand a set of rules which will be useful in converting a particular network into a Thevenin equivalent. Now, to understand Thevenin's theorem, we should first go through the definition. I have written down the definition of Thevenin's theorem here. Now, let us just go through that definition. What is given is that for a linear circuit, it can be only used for a linear circuit. We are going through only linear circuit analysis. Arrange the circuit into two networks, which is network A and network B, connected by two wires. Now, network A is the complex network. Alright. And network B is the network in which we are interested. It is that network in which we will find the power, the current and voltage, etc. And this is the complex network which has to be replaced by the Thevenin equivalent. Alright. So what we have to do? We have to define voltage VOC, that is voltage open circuit, is equal to the Thevenin voltage that appears across A, appears across the network A with B disconnected. This is important. Now you will understand this when we do a simple problem. Then you have to find the Thevenin resistance, which is the equivalent resistance as seen by the network B across the terminal A. Of course, B will be disconnected. And while finding the Thevenin resistance, you have to kill all, I'll add one term here, all independent voltage and independent current sources. Alright. So the question comes, if dependent sources are coming, what we will do? That is a separate topic. In case you are having a dependent source in the network A, you should make sure that the control variable of that dependent source is also in the network A. You cannot have a network, the dependent source in network B and then create a Thevenin equivalent. We'll see that in future problems. Now, to understand what we have learned from this statement, let us do a simple problem, because problems only will help you to understand the theory completely. Okay friends, now this is the problem which we have to tackle. The question is, we have to convert this particular area, excluding the RL. RL is the interested quantity. We have to convert the entire network other than RL into a Thevenin equivalent. So what does the statement tells? First you divide them into two areas, right? You divide them into two networks. One is the network A and the other is the network B. Alright. So that first step is over. You have defined the networks. Next we have to find the voltage VOC which is nothing but the Thevenin voltage, which is the voltage across the terminal of network A. So this is the terminal of network A and this is the terminal of network B, and these are connected by wires. We have to find the voltage across terminal A disconnecting the network B. Alright. So basically what I can do is that I can just copy this entire circuit here. Sorry. I can copy this circuit. I can bring it here. Yeah. What they have asked is that I have to disconnect this particular network B. So I'll just rub it off. So I've disconnected the network B. And then this particular voltage will be the open circuit voltage. And we have to find that value. Now this is a simple problem. See, when the current enters like this, alright, you can use any analysis which you know. No current will be entering the 7 ohm because it's an open circuit. So the entire current will be passing through this area. So the voltage at this point, because there is no drop here, it will be the same as the voltage at this point. So the voltage across the 6 ohm resistance will be the voltage of the open circuit. So what is that? That voltage will be nothing but, with a simple voltage divider, 12 into 6 divided by 3 plus 6. Alright, so it will be 12 into 6 divided by 9. It is going to be equal to 8 volts. Basically now you can see that this is the same problem which I have done using the source transformation. So we can check the values as well. Now you have found out the open circuit voltage. So this is going to be your Thevenin voltage, which is equal to 8 volt. Next, what you have to find, you are having your network B here, alright, disconnected. Next you have to find the Thevenin resistance, alright, and you have to find it as seen by the network B across the terminals of the network A in this particular direction. Alright, so let us see what we will get here. And you have to kill all your voltage sources and current sources. In this case you are having a voltage source, so you have to kill that voltage source. So basically killing in the sense you are going to put a short circuit, and what you will be left with is something like this. Alright, and you have to find resistance equivalent. This is the Thevenin resistance as seen from this direction. So this is 3 ohms, 6 ohms, and this is 7 ohms. Clearly 3 and 6 are in parallel with each other, right? See, you are having one terminal here, you are having one terminal here, and these are common to these two elements. So therefore 3 is parallel to 6. 3 is parallel to 6, and the parallel combination will be in series with the 7 ohm resistance, right? So this is 2 ohms, this is the 7 ohms. Alright, so this are equivalent. So 3 parallel 6 plus 7 will give you how much ohms? 9 ohms. So this is your RTH. That means what we can do is that this network A you can replace by an 8 volt source in series with a 9 ohm resistance. Alright, and this is your load resistance. So this has become your network A, and this is your network B. See, we have replaced this entire complex network into a simple circuit. Now in case you want to find the voltage across the load resistance, alright, voltage across the load resistance, what you have to do, it is a simple voltage divider. So it will be 8 into RL divided by 8 plus 9 plus RL by total resistance, right? Voltage into the resistance divided by total resistance. Alright, so in that case, if you want to find the power across RL, it will be nothing but VL square divided by RL, right? So this is the importance of Thevenin circuits, and this is quite remarkable. I have no other words to it. This is a very important circuit which will reduce the effect a lot. It will reduce the effect of circuit analysis a lot. Alright, in the next session maybe we can start with a little bit of Norton's theorem, and then we will do some problems which are going to help you understand this theory in a much better fashion. Thank you.